So, what we know is that if you have an exponential equation, what we are going to use is if two things are equal, then the log of the first is equal to the log of the second. So that means if the arguments are the same, you can add a log on each side, okay? Or we could take it away. If both sides had a log, then that means as long as it was the log with the same base, the arguments would be equal. So that's what it's telling us in reverse here. So sometimes if we have something where we cannot get a common base, we are going to use this property to either add logs into our problem or take logs away, depending on the situation. So let's say I gave you this problem. We definitely still want to check to see if we can get a common base, because if that works, that is always going to be the fastest option for solving a problem. If I look at this, 8 to the x equals 21. Is there a common base for those? 8 we could write as 2 to a power, but that's about it. Is 21 2 to a power? No. No. So we cannot just get a common base. But what we can do is add a log on each side. Now technically you could do any base you wanted. I am going to stick with either log base 10 or a natural log. Why would I choose those two? Yeah, and those are the two buttons we have on our calculator. So if we're trying to get an approximation, we need the log base 10 or the natural log to plug it in. How does this help me?
It makes it where the log is equal to the log.
It does. Think about properties of logs. What could you do to rewrite this problem now?
Condense it.
Write it in the one form. I forgot what it was. Where it'd be like the base and the equals is the.
Okay, so you could like try to change it to exponential or something. If we just think about log of 8 to the x power, with the properties of our logs, what happens to that exponent? It goes in the front. So if I bring that x down, that gives me x times the log of 8 equals the log of 21. How could I get my x by itself then? Divide log 8. Now when you do that, those logs don't cancel, so don't try that. But we just have the log of 21 divided by the log of 8. If I asked you to give me the decimal approximation on this, then we would go to our calculator. And what does that give us? 1.464. Let's check that. If you go back to the original, so if you do 8 to the 1.4641 power, does it equal 21 exactly? Not exactly, but it's close. Why is it not perfect? We rounded to 4 decimal places. The more decimal places you keep, but the more accurate it will be. However, this is 20.9997, so it's extremely close. So we can still double check on that. Any questions there? Let's look at this one. Three to the 2x equals 1.4. So common base, 3 you can't rewrite. Does 3 to some power equal 1.4? No. So our option is to add a log. So log of 3 to the 2x equals the log of 1.4. It's just one log on each side. If I look at this, properties of logs, what happens?
2x goes to the front.
Now what?
Divide the log.
We need to divide by the log 3 and the 2. So it's all multiplied with the x, so we're just going to divide it over everything we don't want. Right, this is where I see some problems usually trying to plug this into your calculator. It can get a little tricky with all the parentheses. If you go to put this in, so we have log, it opens a parenthesis 1.4 divided by, since I have two things on the bottom, I would have to add a second set of parentheses around this whole thing. So we're going to log, it opens a parenthesis for my 3 and then I have 2 of them to close. So you really have to watch your parentheses on those. If that's confusing to you, the other option, I think we did this when we were graphing rational functions. If you do alpha, the y equals, remember we can have it set up so it's a fraction. And so if that's a little bit easier so you can make sure you have the right thing in the top and bottom, you're welcome to use that feature as well. And then you don't have to worry about the parentheses quite as much. All right, so we get 0.1531. If we check it, go back to the original, 3 to the 2 times 0.1531 power, we get 1.39989. So not perfect because of rounding error, but extremely close. Is that one okay? All right. The property that we're using requires us to have essentially one thing on each side of the equal sign. So I can't just go in and add a log if I have multiple terms on one side. And we want to make sure that we are simplifying things as much as possible before we go trying to add our log. If I look at this one, it's a little bit different because I have two bases on the left-hand side. How could I simplify first? What would I need to do?
You could add the exponents together.
Okay.
And since I have a common base.
Yeah. If you put those together, that means you add the exponents, so that's e to the 4x plus 1. Okay, is there a common base option here? No. So that means we have to add our log. You can do either one. When I see e's, I typically use the natural log. Just a personal preference. It doesn't matter and you will get the same answer either way. I use natural log because natural log is log base e, and I'll show you how that simplifies things in a little bit. What would I do here?
Put the exponent to the front.
Okay, and so now you can divide by your natural log of e, or if you had a log base 10, you divide by log of e, or we can just ask ourselves, natural log of e. Natural log is log base e, so it's saying e to what power equals e? 1. So that's why I like it so much, because when you get a natural log of e, that just turns into a 1. So we have 4x plus 1 equals the natural log of 4. So then we would subtract our 1 we have the natural log of 4 minus 1 all over 4. Again, if you were putting this in, you either use the fraction feature or you need a second set of parentheses around the entire numerator because it's more than one term. So I get 0.0966. Any questions on that one? Everybody got that when they put it in the calculator? Okay, let's try this one.
We add 2 onto the other side and also divide by 3.
Yes, we want to isolate the exponential. Because I could just add a log right now, but if I added a log as it's written, can we break apart if things are subtracted? No, so we can't use our properties of logs and we're stuck. There's absolutely nothing we could do at that point. So first get that exponential by itself. So add over the 2, divide by 3. And then if we have e's, what would we probably want to do? Mm-hmm. Okay, so exponent comes down. Natural log of e is like saying e to what power equals e, so that would turn into a 1. So then to get x by itself, we just have to divide by 5. We get 0.1695. I want you guys to try some on your own. So try the next one. If you get done, I haven't started, but you can try the example 6 as well. So on example 5, can you take this 5 times 3 and make it 15 to the x? Can you?
Yeah.
Order of operations, what do you have to do first? Exponents come before multiplying. So we can only actually multiply them if it's the same base. So we can't. So we have to divide the 5. Is a common base an option? No. 6/5 is 1.2. There's no common base, so add a log. Doesn't matter if you do log base 10 or the natural log. There's no advantage to either one. So the x comes down. So we have the log of 6/5 divided by the log of 3. That's our exact answer if I ask for a decimal approximation. Is 0.16595, so 0.1660. And how can you check yourself on these? Plug them back into the original, it should be extremely close. Alright, this one, what's the first step? Add the 5, and and then divide by 4. Okay, check common base. They still might pop up, and it's faster if you can do that. But 20 is not 2 to a power, so we can't. So we add our log. So the x plus 3 comes down. Notice I am putting it in parentheses because it's that entire thing times the log of 2. There's 2 possible options where to go from here. You can either distribute the log 2 or divide the log 2. What'd you guys do? Divide. So you have log of 20 divided by log of 2. So then what would we have to do?
Subtract 3.
Log 20 divided by log 2 with a minus 3 on the end. And that gives us 1.3219. All right, how did you do on those 2? Good? All right. I want to do 2 last examples for today. So if I'm looking at this one, 5 to the 2x equals 8 to the x plus 1. So it's a little bit different because we have exponents on both sides of the equation. Common base, unfortunately, doesn't work. 5 and 8 don't have anything in common. So we have to start with our log. So the exponent comes down. Notice I put that x plus 1 in parentheses because it's that entire exponent times the log of 8. Now this is where it starts getting a little more tricky because we need to solve for x, but we have 2 of them. So if you have multiple x's, you have to get them on the same side. What am I going to have to do first over here? Okay, you have 2 options. You can either divide the log 8 or we can distribute it. Okay. Either way, we're going to get the same answer at the end. If you divide it, you might have like multiple fractions, like fraction and a fraction when you go to plug it in the calculator, but it's not a huge deal. So it really doesn't matter at all. I think, do you guys have a preference? Divide or distribute? Okay. We divided on the last one, so let's distribute on this one, just so you see both ways. Now when you're multiplying it, that log 8 is like a number in itself, so the x just goes in front. That's our coefficient. And 1 times log 8 is log 8. So we still have multiple x's. We need to get those on the same side.
So could we subtract x log 8?
Mm-hmm. Now, the only way we can actually subtract the logs is if they are like terms, which means the argument is the same. They are not here, so I can't actually combine them. I'm trying to solve for x, so if I can't put those logs together, what else can we do? We can, but I don't know that it'll help us. It'll turn them into exponents, and then you would have a division, but then we still are stuck with trying to get the x.
Possibly divide the log 8 and then divide it by the log 5 or
Okay, right idea, but we need to do something else before that. Because if we divide the log 8 right now, it would go to every single term. So it would help if we had this factored first. What do both of these terms have? So if I factor out the x, So I have x times something. What's the opposite of multiplying? So we get log 8 over 2 log 5 minus log 8. When you put this in your calculator, every time you push the log, it opens a parenthesis, so you have to close it. You also have to realize the denominator has multiple terms, so you would have to put parentheses around that whole thing. Or use the fraction feature on your calculator so you can make sure it's going in exactly as you want it. Did you guys get that? And again, to check it, you would put it back into the original. You would have to put in both sides because there were x's on both. Put them both in your calculator and see if you get the same decimal or very, very close. Does anyone need me to look at how they're plugging things in the calculator if you're not getting it to come out?
Just with the same exact.
Oh, yeah, and it's like 355, and then the decimals are a little bit different. And it's just rounding error. Okay, so walk me through it, guys. Mm-hmm. Then what? And make sure you put the 1 minus 2x in parentheses. Now what? You want to divide? So 1 minus 2x equals x log 4 divided by log 3. What would you do now? Okay, so we could add over the 2x. Now what would you do? No. Okay, if you want to get rid of the fraction, you can multiply the log 3. And we have to factor out an x. So if you're comfortable with the fraction, you can keep it. If you don't like that, then I would recommend on this step instead dividing the log to distribute. But if you ever get to a point where it's ugly like that, you can multiply the log 3 to everything. So totally up to you. But we do have to take out the x. And now to get x by itself, you would divide. So we have this beautiful thing to plug in. If you had done it the other way with distributing or decided at some point you wanted to multiply your log 3, it would have looked like this. So these are equivalent depending on which way you did it. But let's get our decimal. We should get 0.3066.